Hello everyone, in this video we will discuss deformation, retractions and homotopy type. So firstly we define homotopy type. Now let us take two continuous maps, one from x to y and other is y to x. So let f from x to y and g from y to x, these be continuous maps. Now if G circle F and F circle G, both the compositions are homotopic to identity maps, then we say F and G are homotopy equivalences. So if F circle G is homotopic to identity map of Y and G circle F, it is a homotopic to identity mapping of X. Then F and G are called homotopy equivalences. And each of F and G is called homotopy inverse of the other. So basically, when we say that G circle F and F circle G both are equal to identity, then we say they are inverses of each other. But here they are not equal, they are homotopic to identity map. So we will call them homotopy inverses of each other. Now this homotopy equivalence, this is basically equivalence relation. If we take F from X to Y, which is a homotopy equivalence of X with Y, which means for the mapping F from X to Y, there exists some mapping F dash from Y to X, which is homotopy equivalence of F. And if we take another mapping, let us say H from Y to Z, which is also homotopy equivalence of Y with Z, then the composition H circle F from X to Z, that is a homotopy equivalence of X with Z. So it means it is equivalence relation. This homotopy equivalences, this is equivalence relation. And if two spaces are homotopically equivalent, now if F is F and G, they are homotopy equivalences, then these two spaces X and Y, they are called homotopy equivalent. And X and Y are called homotopy equivalent. So if two spaces are homotopy equivalent, then we call they have same homotopy type. So Now we can easily check that if a space, subspace A, is a deformation retraction of the space X, then A has the same homotopy type as X. If A is a deformation retraction, A is a deformation retract of X, then A and X have same homotopy type. A and X have same homotopy type means we can define a mapping A to X and another mapping from X to A such that the compositions, both the composition of those two mappings, they are homotopic to identity. So this we have earlier proved that if A is a deformation retraction and if we define J, the inclusion map from A to X, and we define R from X to A, the retraction which is given by deformation retract, then J circle R, this is equal to identity map, and R circle J, this is, J circle R, this is homotopic to identity map, and R circle J, this is equal to identity map. So we can define two mappings, one from A to X and other from X to A, such that both the compositions are homotopic to identity. So we can say they have same homotopy type. Now in this lecture, we will prove that two spaces having same homotopy type, they have same or isomorphic fundamental groups. So firstly, we will study that whenever we have a homotopy between two continuous maps of X into Y, such that the base point of X does not remain fixed during the homotopy, then what will happen? Because we have studied already under the topic of deformation retraction that if we have a homotopy between two maps from X to Y such that the homotopy remains fixed during the homotopy, such that the base point remains fixed during the homotopy, then the homomorphisms of fundamental groups generated by those two maps, they are equal. So now let us see what happened when this point does not remain fixed during the homotopy. So we have firstly this lemma. So if H and K, these two are continuous mappings from X to Y, and let us take point X naught goes to Y naught under the mapping H, and the point X naught goes to point Y1 under mapping K, means it does not remain fixed. And if H and K are homotopic to each other, then we have to prove there is a path alpha in Y from point Y0 to Y1 such that the homomorphism K star can be written as a composition of alpha cap and H star. So if the base point remains fixed, then K star is actually equal to H star. But if base point does not remain fixed, then K star is equal to alpha cap circle H star, where this alpha cap, this is homomorphism generated by the path alpha from Y0 to Y1. And in fact, we can prove that if capital H is the homotopy between this H and K, and obviously that will be a mapping from X cross I to Y. And if this is homotopy between H and K, then this path alpha, this is defined by H of x naught t. So this can be associated with the previous lemma in which we have proved that for the uh, where the base point x naught remains fixed, then k star and h star, they are same. So now here h of x naught t, this is not a constant, but it is the path alpha. So that's why k star is given by alpha cap circle h star. So in this case, basically, we have this type of diagram of arrows. So this is fundamental group of x with respect to x naught, fundamental group of y with respect to y naught. Now this is mapping h star because h is a mapping from x to y, which maps x naught to y naught. And here we have fundamental group of y with respect to point y1. And now this is k star because k is a mapping from x to y, which maps x naught to y1. Now this is alpha cap because alpha is a path from y naught to y1. The alpha cap is homomorphism induced by alpha from fundamental group of y with respect to y naught to fundamental group of y with respect to y1. So we have to prove basically this diagram is commutative. That is k star is equal to alpha cap circle h star. So now domain of both of these mappings, k star and alpha cap circle h star, that is fundamental group of x with respect to x naught. So we have to uh, prove that these two mappings are equal on path homotopy classes of paths, uh, paths based at x naught in space x. So let us take firstly a path f, which be this is a loop in x based at point x naught, so that its homotopy class belongs to fundamental group pi 1 x x naught. So we have to prove basically this thing, k star of this f, this is alpha cap of h star f. That means we want to prove that k circle f, its homotopy class, this is alpha cap h circle f, and the definition of alpha cap is basically alpha bar star h circle f star alpha, where alpha bar is the reverse of path alpha. So we want to prove this. So we consider now two loops, f naught and f1. Now, what is f naught? F naught is a loop in space x cross I, and similarly f1 is also a loop in space x cross I, and these are defined by the equations f naught at s, this is fs0, and f1 is defined by fs and 1. Now we consider a path C again in the space x cross I, which is defined by C of t, this is x naught t. So basically we have defined all these things like in this diagram. Now we have this I cross I, now let us say this is our space x, so this is basically x cross I, and say this is a space y, Now we have defined F0 and F1 and C, three paths in space X cross I, and they are defined by F0 is given by f of s 0. So this will be our F0. This is point x0 0. Now because F is a path in space X. Now this base of this cylinder is basically the space X. And if this is path F based at point x0, and we have defined F0 to be same path F, but in the base of the cylinder. So this is path F, which is in the base of the cylinder, which means this is F naught, which is based at point x0 0. Similarly, F1 path, that is the path basically which is same as path F, but not in base, but in the top of the cylinder. So this will be our F1. And this point is x0 1. The path F1 that is based at x0 1. So this also makes a cylinder here because the path F is also same, and this is called F0 in the base, and this is called F1 in the top of this. And we have defined C, this is x0 t. So C, as t goes from 0 to 1, image goes from x0 0 to x0 1 along the straight line. So this straight line joining these 2 points x0 0 and x0 1, this is our path C. Now here, image of this point x0, that is somewhere here y0, and image of this point here, that is y1, because we know H is a mapping from x to y, which maps x0 point to y0, and k is a mapping which maps x0 to point y1. So let us say these 2 points are y0 and y1, and now we have a path alpha from y0 to y1. Then H circle F. Now because F is a loop based at point x0, then H circle F, that is a loop in space y based at point y0. And similarly, K circle F, since F is a loop in x based at x0, so K circle F is a loop in y based at point y1. So this is our diagram. Now in this case, we assume that H is a homotopy, capital H, that is a homotopy between H and K. So that means H is a mapping from X cross I to Y. And we know under this homotopy, what is H circle F naught? H circle F naught, this is basically H of Fs naught and H of x0, that goes to small h of s. So it will be H circle F of s. So we can say that H circle F naught, that is basically small h circle F. And similarly, we can prove that H circle F1, this is K circle F. And thirdly, H circle C. Now this H circle C, now since C is a path given by Ct is equal to x naught t, then what is H naught, H circle C? H circle C of t, this is H of x naught t. Now since H is a homotopy between H and K, so H of x naught t, that is basically alpha t, because in the statement of this lemma we have assumed that alpha is the path given by h of x naught t. So h circle C is alpha. Now this thing here somewhere we have h circle F, and this is h circle, this is k circle F, this is h circle F based at point y0, y1. Now we define capital F from I cross I to x cross I by the map f of st, that is fst. F of st is fst. So that will be basically mapping this whole area I cross I to x cross I, but actually this whole area is mapped to this cylinder, which whose base is f0 and top is f1. And we define these four edges of I cross I by, let us say this is beta naught, this is beta 1, this is gamma naught, this is gamma 1. The four edges of this I cross I, let they be defined by beta naught, beta 1 and gamma naught, gamma 1. So we can define like this: beta naught S, this is S0, beta naught, beta 1 S, this is S1. These are basically paths. Beta naught, beta 1, gamma 1. These are four paths which run along the four edges of I cross I. So all these are basically mappings from I to I cross I given by this gamma naught at t, that is 0t, and gamma 1 at t, that is 1t. So let these be defined like this. Now what is image of beta naught under capital F? So let us check. Beta naught S, so f of S0, and f of S0 by definition of capital F, that is fs0, and fs0 is our path f naught. So we can see here that f circle beta naught is f naught. Similarly, we can prove that f circle beta 1, this is f1, and f circle gamma naught, this will be C, and f circle gamma 1, this will be C when we check all of these. So by diagram, basically we can see that under the mapping capital F, now let us say this is capital F, under the mapping capital F, this path which starts from this point to this point along this straight line beta naught, that maps to this f naught under this capital F, and beta 1 maps to f1 under capital F. So gamma 1 and gamma naught both are mapped to C, this edge of the cylinder C. Now these four, beta naught, gamma 1, beta 1 and gamma naught, these are broken line paths. And if we take the product of beta naught and gamma 1, now this beta naught and gamma 1, now this product, this is basically path starting at point this 0 0 and ending at point 1 1. Similarly, this product gamma naught star beta 1, this is also a path starting at point 0 0 and ending at point 1 1. Now, because this box I cross I, this is convex set, and we know any two paths starting and ending at same points in a convex set, they are homotopic to each other. So these two paths are homotopic to each other. And let us say capital G is a homotopy between them. So we can see here that the paths beta naught star gamma 1, and gamma naught star beta 1. These are paths in I cross I from point 0, 0 to 1, 1, and basically I cross I is convex. So these two are homotopic. Beta naught star gamma 1. This is homotopic to gamma naught star beta 1. And suppose G is the homotopy between them. And if G is a homotopy between them, then what is F circle G? Now F circle G is a homotopy between F circle beta naught star gamma 1 and F circle gamma naught star beta 1. And F circle, this is the path basically F circle beta naught star F circle gamma 1. So F circle beta naught is F naught star F circle gamma 1, that is C. So second one is F circle gamma naught, that is C. F circle beta 1, that is F1. So F circle G is a homotopy between F naught star C and C star F1. Then we take the composition with capital H. Then capital H circle F circle G. This is a homotopy between, obviously this is a homotopy in Y. So this is a homotopy between H circle F naught star C and H circle C star F1. Now what is this map? H circle F naught. H circle F naught is H circle F and H circle C, that is alpha, and H circle C star F1, so it is H circle C, so it is alpha. H circle F1, that is K circle F. So this is a homotopy between this and this. So now here we have proved that H circle F star alpha, this is homotopic to alpha star K circle F, which means H circle F star alpha, their homotopy class, that is equal to alpha star K circle F, which means a homotopy class of K circle F. If we multiply alpha bar on left hand side of both sides, then alpha bar star alpha, that becomes identity, and the left hand side becomes alpha bar star H circle F star alpha. So this we want to prove. So it means our K star is basically alpha cap circle H star. Now this lemma has some corollaries. Now if in this lemma, if we take H and K to be homotopic continuous maps such that H of x naught is y naught and K of x naught is y1, and if we assume that H star is injective, then so is K star. Similarly, if H star is surjective, then K star is also surjective. If H star is trivial, then K star is also trivial. Because we have proved K star is equal to alpha cap circle H star. Now, if H star is injective, since this alpha cap is an isomorphism, so this alpha cap is a homomorphism, and if H star is injective, then K star will be injective. Similarly, whenever H star is surjective, K star will be surjective. And if H star is trivial, then K star is also trivial. Now the second corollary says if H is a mapping from X to Y, which is null homotopic, then H star is trivial. So if H star is null homotopic, that means H star is homotopic to constant path. So here we can take K to be the constant path. Then K star is equal to alpha cap circle H star. But K is constant, so K star is trivial, which means H star is trivial. So now we come to main theorem. And this theorem says if we have a homotopy equivalence from X to Y, then the fundamental groups of the path of the space X and fundamental group of space Y, they are isomorphic to each other. So let us take F to be a continuous map. Let this be continuous map, and it maps X naught to point Y naught in space Y. Now, if F is a homotopy equivalence, then we define mapping F star from pi 1 X X naught, the homomorphism induced homomorphism of fundamental groups. This is an isomorphism. So let us prove this. Now, since it is given that F is homotopy equivalence, so there exists another mapping G from Y to X such that G circle F is homotopic to identity, and F circle G, this is also homotopic to identity map. G circle F is homotopic to identity map of X, and F circle G is homotopic to identity map of Y. Now we consider this map X X naught to Y Y naught. This is our mapping F, because it is given that F maps point X naught to Y naught. Now we have a mapping G from space Y to X. So let us say this mapping G maps point Y naught to point X1. Then further, we define mapping F, which is already defined from space X to Y. So under this mapping F, let us say this point X1 is mapped to point Y1 of space Y. Now here basically we are taking X1 is G of Y naught and Y1 is F of X1. So correspondingly to these three continuous maps, correspondingly we have these induced homomorphism. One is from pi 1 XX naught to pi 1 YY naught. This is our F star. Now we will call this mapping Fx naught star. Now because we have two mappings, we consider two different mappings F. One F is from XX naught to YY naught, and other is from XX1 to YY1. So this is the homomorphism induced by F, which is corresponding to the point X naught. And now we have this G XX1. So this is our G star. And then further from this to pi 1 YY1. Now this is mapping Fx1 star. So this is the homomorphism induced by F relative to point X1. Now we have these three homomorphisms. Now we know G circle F is homotopic to identity. That is given to us. Now this G circle F is basically a mapping from space XX naught to XX1. So this is homotopic to identity map. So G circle F star, because of the lemma, in the lemma we have proved that if H is homotopic to K and H mapping maps point X naught to Y naught and K maps point X naught to Y1, then K star is equal to alpha cap circle H star, where alpha is a path from Y naught to Y1. Now in this case, this G circle F is a mapping which maps X naught to X1, and identity map maps point X naught to X naught itself. So we can define a path alpha in X such that G circle F star, this is alpha cap circle IX star. Now this IX is basically identity of X. So alpha cap star, alpha cap circle identity star. Now identity star is identity mapping, and alpha cap circle identity mapping is just alpha cap. what is this G circle F star? This G circle F star, this is basically G star circle F star. Now here we are using F star as basically Fx naught star. So we have proved that this composition is equal to alpha cap, and alpha cap is an isomorphism because alpha is a path in space X from point x0 to x1. So this is isomorphism. And secondly, F circle G, that is also identity, that is also homotopic to identity map, but that is homotopic to identity of Y. Now this means the homomorphism F circle G star, again in the similar manner we can prove that this is Fx1 star circle G star. This is also isomorphism. So from this fact, if the composition is an isomorphism, then the later mapping G star, this will be surjective. So this G star is surjective. Sorry, this thing, G star circle Fx naught star, this is isomorphism. Therefore, this G star is surjective. But from here, Fx1 star circle G star, this is isomorphism. It means G star is injective. So it means G star is isomorphism. Now from the first equation that this is an isomorphism, then we can conclude that Fx naught star, this is G star inverse circle alpha cap, because G star is in isomorphism, so we can take its inverse. Now this is isomorphism, this alpha cap, this is isomorphism, so composition of two isomorphisms, that is also an isomorphism. So Fx naught star, this is isomorphism. It means pi 1 xx naught, this is isomorphic to pi 1 y naught, and this we want to prove. Now in this theorem, one more thing we want to say, that G is a homotopy inverse. We have said that F and G both are homotopy equivalences of each other, means G is homotopy inverse of F. But still, the homomorphism G star is not inverse for the homomorphism Fx naught star. So we have proved basically this thing, Fx naught star is G star inverse circle alpha cap. So from this we can say that G star and Fx naught star, they are not inverses of each other.